So we have discussed already up to the kinematics of the circular motion, and before starting the dynamics of circular motion we require some concepts of another topic, that is work, power, energy. Now first of all, I want to ask you two questions. First, what is the main utility of Newton's second law of motion? What is the main utility of Newton's second law of motion? Why this law is very famous? So famous, this law is so famous, but what is the reason behind it? No. For only acceleration you have defined it, kinematics, that has nothing to do with Newton's second law. Then why Newton's law's second law particularly very famous? But that's not okay. Have you ever think of it? Why Newton's second law is so famous? See, suppose we consider only the constant mass problem. Even for constant mass problem, we consider a single particle and write Newton's law in this format. I consider the one-dimensional motion. In that case, this can be written as MA, that is M divinity is called the acceleration. F can be written as M dv dt. Then if you know F as a mathematical function, then you can integrate and find V as a function of time. And when you get V as a function of time, by integrating you can find the position of the particle as a function of time. So Newton's law gives us the force which is related to acceleration. Then by a single integration you can find the velocity of the particle. By another integration you can find the position of the particle. Provided initial velocities and initial position of the particles are given, then you can find the final position and final velocity of the particle by applying Newton's law. Means you can predict what will happen to this particle in future if it is acted upon by a particular force. So that means this is a future involvement of the system or the particle. Means how the particle moves. That future of the particle you can completely predict once you know Newton's law with initial velocity and initial position. So that's why this law is very famous. Now see, though this law theoretically gives us all the answer to all the questions of mechanics problem, there is certain difficulty in this law. Because actually in case of a 3D motion, this force is a vector quantity. Then it is difficult to find out the vector, this vector. Suppose a wheel is rolling over a horizontal surface. How many forces are acting on it? How many forces are acting on it? Weight can act in vertically downward direction. In vertically upward direction, normal reaction can act. Friction can act. Now think about it. Any other force can act. If I tie the wheel with a string and pull it, and tension of the string will also act. Moreover, the point of contact of a wheel moving over, rolling over a surface, is the point of contact a single point, or there are many points in contact? Many points in contact actually, because at the junction, due to huge pressure, some portion is actually compressed And as a result, there are many contact points, and through each contact point normal reaction may act, and even the wheel which is moving is not perfectly a rigid body. So that's why normal reaction will vary with different position. So now in this complicated scenario, by applying Newton's law, this F makes vector sum of all the forces, external forces acting on the particle. Now it is always possible that you left some force to calculate, or you cannot calculate some force as a proper mathematical function, and you missed it and you cannot write Newton's law. So even if Newton's law is highly successful, at least according theoretically, but when we are going to practically apply Newton's law and to identify the force, we are in great trouble, because there are so many forces on a particle or on a system, and this situation may arise that we cannot identify all the external forces. Then in that situation, how can we solve the problem? When Newton's law cannot help us to solve the problems, then how can we do it? We will consider another limitations of the Newton's law. Newton's law is acting used for mechanics problems. Now, can we apply Newton's law for solving the problems of current electricity? No. But there is a formulation of the mechanics in terms of some other thing other than Newton's law, force, all these things, which can be used for solving the problems of current electricity also, or for solving the problems of thermodynamics, because Newton's law is not also applicable in thermodynamics. So though Newton's law in principle can solve all the problems related to mechanics, we require some more deeper insight into the mechanics problems by involving some other quantities. So first, the thing comes, why Newton's law is difficult? Because it deals with a vector. Force is a vector quantity, and vectors have components in 3 dimensions. They have 3 components. So they are multi-component systems, the numbers, multi-component objects. So we have difficulty in discussing them. Now we try to formulate the mechanics in terms of some scalar, because scalar has only magnitude, no direction. So only one equation is sufficient to express the scalar. For vector, we require 3 equations. For each component, 1 equation. For x component, for y component, for z component. For each component, 1, 1, 1. That is 3. Now we try to formulate mechanics entirely in terms of some scalar quantity. Scalar means only magnitude, no direction. So only one equation is sufficient to describe all these mechanical problems. What is the name of that scalar? That particular scalar is called the work done. So work done, in terms of work done, we can also solve mechanics or mechanics problems, and this is completely equivalent procedure to solve mechanics problems apart from Newton's law, where Newton's law gives us a vector formulation to solve the mechanics problems. The work power energy, this topic, or the work done, gives us a scalar formulation of the mechanics, which is much more easier because we don't have to deal with the directions. Okay, so that's why this work power energy, this topic is so important, and we have to study this first. Is it clear why work power energy as this topic is so important? Now, the basic things of work power energy will again come from the concept of Newton's law, because earlier we studied only Newton's law. Now, first we define work done by a force. on a single particle. We consider that an object is here and we apply a force F. This force is constant in magnitude. This force is constant in magnitude and also constant in direction. And we consider the body is moving under the action of this force along this horizontal direction. So we consider after certain time the displacement of the body is here up to here. So the displacement of the body is denoted by another vector quantity called displacement S. So S is the displacement of the body under the action of this force. We consider that the angle between displacement vector and the force vector is theta. This angle is considered as theta. Now, due to this force, when the body moves from this point to this point, the point of application of the force changes the position. Point of application is earlier at this point, now it is at this point. The point of application of the force is moving due to the action of this force. Now, is the point of application of the force moved in the direction of the force? No, because if it moves in the direction of the force, the body must move along this line. Is it moving perpendicular to the direction of force? No, then it must move along this. It is moving in oblique direction at an angle theta with the direction of force. Then I have to find out the component of force along the direction of displacement. Okay, because point of application of force moves, and what will be the component of force along that direction in which the point of application moves. So point of application moves here along S, so we can find the component of force along S by dropping a perpendicular from this point on the direction of S. Then tell me, what is the length of this part after this? Obviously L cos theta. This one is base, this one is hypotenuse, so base will be hypotenuse times cosine theta. So F cos theta is the component of force along the direction of displacement of the object. That means along the direction of displacement of the point of application of the force. Clear? So work done is defined by component of force along the direction of displacement multiplied by magnitude of displacement. Component of force along the direction of displacement multiplied by magnitude of displacement. Okay, so this is defining the work done. Now, someone can say that you are taking the component of force along the displacement and then multiplying with the magnitude of displacement. I want to take component of displacement along direction of force and then multiply it by magnitude of force. So we will simply write this one as S cos theta times F, means he wants to take the component of displacement. So this is displacement vector, So its component along the direction of the force is S cos theta. And he is saying that I will take component of displacement along force multiplied by magnitude of force. So should I get the different result or we get the same result? Same result means whether you are taking component of force along displacement or the component of displacement along force, the result of work done will remain same. Means work done does not depend on direction. So it is a scalar quantity. So this one is also W, and we can write this one as F dot S. This one can be written as S dot F, and earlier we have seen that dot product between two vectors is commutative. So since they are commutative, so F dot S should be equal to S dot X. So work done by no means depends on direction. Yeah, work done does not depend on direction. So it's a scalar quantity. It is just defined by the dot product of force and displacement. Okay? Now, we will discuss three cases. First one, suppose if the body moves along the direction of displacement, if the body moves and the force is along the direction of displacement, force is along the direction of displacement. What is the angle between force and displacement? 0 degree. In that case, the first situation that arises, it will be theta equal to 0 degree. Means you can write W equal to simply F into S. Okay, F into S, because cos 0 is 1. Now we consider the second situation. When force and displacement are oppositely directed to each other. Force and displacement are oppositely directed to each other. In that case, what is the work done? Minus Fs. Okay. Give me one example of this negative work done. One example of the negative work done, that force is acting in some direction and displacement is in opposite direction.
Electric potential wings. Electric potential.
But give me some example which is very electric potential is not a vector. Some common example. Any common example where work done is negative? Work done by friction force, that is always negative, because if you try to pull a body, friction will be in the opposite direction. If the body moves along this direction, the friction is always opposite. So what is the angle between friction force and displacement? Always 180. So cos 180 will become minus 1. So work done by friction force is always negative, because whenever you try to pull some object, the friction will be acting in the opposite direction. So angle between displacement and force is 180. So work done becomes negative. Another common example. Suppose I pull this marker upward. So what is the work done by me? Suppose I put the marker in the upward direction. So work done by me in pulling the marker upward, is it positive or negative?
And starts it in that last.
I pull this marker from this point upward. What is the work done by me in pulling the marker upward? Is it positive or negative?
Listen.
First tell me in which direction force acts.
What is the back?
Upward, because I am pulling. So that pulling force is in the upward direction. Displacement of the marker is also in the upward direction. So work done by me is positive, because force and displacement both are along the same direction. But in the same case, if someone asks you what is the work done by the weight of the marker, that is gravitational force, that is negative, because gravitational force means weight. It is acting and it is moving. So angle is non-active. Work done by gravitational force is
Direction.
so you learn from this example one thing, that in a particular case this marker is actually moving up. This is only phenomenon. But how we can describe it? If we want to find the work done by applied force by me, then it is positive. If in the same situation I want to calculate the work done by gravitational force, then it should be negative. So it is not that this work done, it is moving up, so you cannot say that work done is positive or work done is negative. This, if you are saying that work done in moving this marker is positive, this statement is wrong. You have to tell for which force you are calculating work done. Whether you are calculating by the force given by me, or you are calculating the work done for the force of gravitation. So that has to be mentioned. So the name is work done by a force, not in general that work done. If you are saying that if it is moving up, so work done is always positive, then it is meaningless. For which force you are calculating the work done, that has to be specified, because changing the force will change the magnitude of work done even for same displacement, same phenomena. See in this case, due to my applied force, work done is positive. Due to the gravitational pull, downward, moving upward, the angle 180, work done becomes,
And like it.
the situation is same, the marker is moving up. Okay, so don't say that work done. Always say work done by a force. You have to specify the force for which you are calculating work done. Is it clear?
So we can.
Next. So the second point comes, that is theta equal to 180 degree, work done W equal to minus of Fs. The third situation, that is when force and displacement are perpendicular to each other, we get cos 90. Cos 90 will become 0. So we can write number 3, when theta equal to 90 degree, work done will become C. An example,
Something is there in reverse.
pulley
That is like this one.
pulley carrying a luggage over his head and moving like this. So he is not doing any work.
That's moving no instrument.
So we must not give any money to the pulley,
That's me.
right? According to you. So in the train station or anywhere you put your baggage and luggage and all these things over the pulley's head, and now you are showing, okay, in physics class I learned that you are moving horizontally. So I will, your work done will be 0 and I will not give you a single rupee.
Because
Right?
then
See, most of the time, this one is given as a very funny example of the calculation of the work done. But what you are saying is completely wrong. pulley is doing what? Work done by the pulley is not zero.
It is one is in sound thinking, but what
How?
that's less than it
Yes?
because less than 90.
That
Exactly less than 90.
angle 90, so that's why coming zero.
That's less than 90.
Theta 9 less than 90. No, theta equal to 90. But pulley is doing work. How? See, work done is specified for a force. So when the pulley is taking the luggage in the head, then the weight of the luggage is in which direction? Downward. And with respect to the head, is the luggage moving? No. So the displacement is zero. That's why work done is zero. But is the pulley is doing the work? Of course he is doing the work. Why? See. Previously, suppose the mass of the pulley is m. So while he is moving, his normal direction will be mg.
It's here.
N equal to mg. And we know that for the movement, the pulley has to overcome friction. So friction F equal to mu n, that is mu mg. Now the pulley is taking the luggage over his head. So what is the total normal direction of the pulley? Mass of his own body plus mass of the luggage, that is m plus m into g. So the normal reaction force increases, and if the normal reaction increases, you know that friction will also increase. So pulley has to overcome more friction, so he has to do more work. Pulley is doing work, but the gravitational force is not doing work, because gravitational force of that bag is downward and he is moving forward. So work done by gravitational force is zero because they are 90. Movement and the force are 90 degree because weight of this bag downward, pulley is moving in this direction. So bag is also moving horizontal, angle between them 90 degree. So work done by the gravitational force is zero. But work done by the force exerted by the pulley is the muscle force to overcome the friction, and since in this case friction increases, so he has to work more. So these are the three special cases, and in this situation we consider when force and displacement are perpendicular to each other, force is called a no work force. There is another concept called the zero work force. In either situation, work done is zero. For no work force, force and displacement, none of them are zeros, but they are perpendicular to each other. So cos theta will become zero. But for zero work force, suppose this one, you are applying a force on this wall, and you are not able to move this wall at all, then displacement is zero. So that's why work done by this force is also zero. So this is called the zero work force. So zero work force will produce zero work, W equal to zero. For no work force, W is also zero. But the situation is different. Zero work force means displacement. That's why work done. No work force means force and displacement are perpendicular. So cos theta becomes zero because it is cos 90. That's why work done becomes
Sing.
clear? Now.
Definitely use out of this state that couple is fabulous. Explain the same. Though these are both. Things about what the work is doing them. You see. And it gets ways in the city. It seems that it's what you're doing, but it think let's things like anything schools was 100% in great things too.
There is some block of mass say 2 kg, acceleration due to gravity given 10 meter per second.
Okay.
And this mass is
Listen.
taken up, moved up to a height
And listen. như vậy là cái vật của không
5 meter above the ground. This mass is moved up to a height 5 meter above the ground. Okay?
it is best
Then calculate the work done by the gravitational force, that is weight of the mass. Then find the work done by the gravitational force
I thought it is
on this mass.
the minus time that we need to see in the odds right connection at it's where it's gonna be down let's be really sure the church will be so we should have a fight just go with
Find the work done by the gravitational force on this mass.
the
See, what is the displacement? 5 meters. You can calculate the weight of this mass. That is, mass is given, g is given. Then find the gravitational work done by gravitational force.
here it comes tree just basically
Force is mg and displacement s. Let's calculate work done force into displacement. What is coming?
negative
100
is 1 like there is negative sign
minus 100 joule. Unit is joule, Newton into meter.
so was it equals the continuous box the improvement and potential
Just force into displacement. Force is how much? 5 into force is 10 into 2. That is 20. 20 Newton in downward direction. And displacement is 5 meter in upward direction. So angle between them is 180 degree. So minus sign will come and 20 into 5 means 100. Is it clear? So this one is coming minus 100 joule. Because I put it in this equation, W equal to F is mg,
is
displacement S cos 180. So it will be minus m is 2, g is 10, S is 5. So it is coming minus 100 joule.
is
Now I am asking you another question. Right now,
there's nice
what is the work done
this is cut
by the
done is
force applied by you? What is the work done by force applied by you to pull the mass up to a height 5 meter?
is this
Now see why I am giving this question. Second part. The body is on the horizontal surface. On its own effort, it cannot move up to 5 meter. Due to the weight, it cannot move. So definitely some external agent, some pull it, must pull it such that it will move up to this height. See, this duster is here. Duster is that mass supposed to get. Its weight is acting downward. So if external agent will not apply any force, duster will not go up. So you have to pull it upward. So what is the work done by the force applied by you in this case?
you want ready for the text
What is the work done by applied force
is height
in moving the duster 2 meter upward, 5 meter upward?
let's get on one heart rate
Any other? What is the work done? You are applying some force in the upward direction, so that's why it is moving up. So what is the work done by that force applied by you?
slaves,
Anyone?
body,
Plus 100.
each what you do,
Okay.
and get seriously, but
Others? What do you think? Is it plus 100 or not?
in the sense, in front of it, one second. One with the physical body.
It may be plus 100. It may be some other level. How?
Now look,
That depends on the situation. Whether the mass is moved up to 5 meter height with constant velocity or with acceleration. If it moves upward by a force such that its movement is with constant velocity, then the work done by that force should be plus 100 Newton, plus 100 Joule. But if it is moved with acceleration, then it will be not be plus 100. It is more than that. So minimum, how much required? Plus 100. And it may be more than that. It depends on how much acceleration you are moving into the upward direction. Now why this terms?
really, when you know you want to do something,
Any idea? If we move this body with acceleration, then why the work done is greater than 100 plus 100?
we can see effective initiatives, but right now,
More insight, physical insight is required. If you are moving with constant velocity, then work done by your applied force is also plus 100. But if you are moving with acceleration, then work done by your applied force is greater than plus 100. But
reverse.
more force, of course, and due to this more force, the body will accelerate. If you are applying a force in the upward direction whose magnitude is greater than mg, then the body will accelerate, and then work done becomes greater than plus 100. Because the body gains velocity, the velocity of the body increases in that case because of the acceleration. And since the velocity magnitude is increasing, the kinetic energy will enter to the system. So that's why if you are applying more force, the kinetic energy of the system will change. That actually comes from work energy theory. That this excess quantum equal to increase in kinetic energy of the mass. So the mass's kinetic energy will now increase if you try to pull this object with a force greater than mg. That means the body is going to 5 meter in an accelerating manner. Accelerating manner is velocity increases. Velocity increases means kinetic energy will increase, because kinetic energy is defined by half m into v square. So if the velocity magnitude increases, obviously kinetic energy will increase. Okay, so right now, if the body is taken up to 5 meter height, if the body is taken up to 5 meter height with constant velocity, with constant velocity, then work done by applied force is plus 100 Newton, plus 100 Joule, plus 100 Joule. Okay? But if it is moving up,
well,
with acceleration, if it is moving up with acceleration, then force is more, upward force is more than weight. Upward force is more than weight.
You would take at the great stop, I shot. And like that.
As a result, work done by applied force is greater than plus 100 joule. Work done by applied force is greater than plus 100 joule.
This stuff is unbelievable.
So due to acceleration, velocity, magnitude of velocity increases. So due to acceleration, in this case, so due to acceleration, right now, so due to acceleration in this case, magnitude of velocity increases.
It always takes some time to look.
Magnitude of velocity increases because direction is still remains same in the upward direction, but the magnitude of velocity increases. Means kinetic energy of the system will increase. Kinetic energy of the system will increase.
This guy.
Okay, so if the object is accelerating, means accelerating, and this acceleration comes through increasing magnitude of velocity, then kinetic energy will increase. Repeat. Okay. Since the body is accelerating, due to increase in magnitude of velocity, the kinetic energy of the body will increase. Kinetic energy of the body will increase. Okay? Now,
What?
so first we will consider only those situations where kinetic energy of the body will not change. Okay, means whenever the body moves with constant speed. Constant speed means the magnitude of velocity will not change. So we will discuss one more situation over there.
What?
Now check.
Thank you.
If I replace this body by a mass m,
Let's try. Please.
the weight is mg. I apply a force along this direction to move it up to height, say h. Move it up to a height h.
Well, you are student.
Then how this movement occurs? With constant speed. No change in speed. Direction is also fixed in this case. So right now, the situation again, replacing this 2 kg, this numbers by simply symbols
And explain
m.
why I need to do good work.
I want to move it up to height h with constant speed.
She will be
Okay? Now, constant speed means if I write Newton's second law for this mass, F should be equal to mg. Constant speed means no net force. So the net force balances. So for constant speed,
let's get that. Thank you, my ABC.
F should be equal to mg in magnitude.
Let me go on.
Then we calculate the work done by
This is I.
applied force. Applied force is F. Then we can write magnitude of F is mg, upward direction movement displacement is h, and angle between force and displacement is 0 degree. Angle between force and displacement is 0 degree. Because F is upward, h is upward, displacement upward, and angle between them 0 degree, and magnitude of F is mg, because we consider constant speed. So mg, h cos 0. So the answer will be mgh. Now you can also see you derive the formula for potential energy also. mgh. It is only coming from the definition of the work done. Now, I want to calculate the work done by gravitational force. Suffix mg. Work done by gravitational force. So what is mg? Magnitude of the gravitational force, mg. The magnitude of displacement h, but the angle between them is 180. Because weight is downward, this one is upward, so angle between them is 180. So it will become minus mgh. Now you can say that this body is acted upon by two forces. One is F upward, another is mg downward. But the net force is 0. Then if I calculate Wf plus Wmg, means work done by all the forces acting on the body. Work done by all the forces acting on the body. What will be their sum? 0. And that comes only due to constant speed. Work done by all the forces will be 0. Now, if someone asks you that can we calculate the work done by all the forces in a different manner? Here I calculate the work done for individual forces and then we add them to get 0. And now we are claiming that since it is moving with uniform speed, I can calculate the work done by calculating work done for individual objects and then adding them I will get 0. Can we do it separately? By not calculating work done for each of the forces, we can do it. How? Since the body is moving with constant speed, what is the net force on this mass? 0. Because F is upwards, mg is downward. So F net will be F minus mg. That is 0. So what is the total displacement? H. So net force into displacement is also 0 into h. That is. So this work done can as well be calculated as first calculating the net force. Then multiply this net force with displacement. Net force into displacement. Here displacement is h into cos 0 degree or 180 degree, whatever you can think. But what the total work done you will get? 0. Because in this situation, since it is moving with constant speed, F net equal to 0. So as long as speed is constant, or we can consider the net force 0, then speed is constant in linear motion. In a linear motion, speed constant means net force 0. Okay, so we can calculate the work done by two methods. You can calculate the individual work done by individual forces and then add them to get total work done by all the forces 0, or calculate the resultant of all the forces and then multiply it by displacement, because resultant of all the forces in this situation, since it is moving with constant speed, is 0. So 0 into displacement will become 0. So two methods. Either calculate work done for each individual force, then add. Some will be plus, some will be minus, and some will be total sum which will be 0. Or calculate the force first, it will give us 0, then multiply 0 with that displacement, it will give you 0. Clear? So two techniques are there. Either calculate work done for each forces and then add, or calculate the addition of each forces first, then multiply it with displacement to find work done. Both are identical as long as the particle is moving with constant speed. Is it clear to everyone?
Yes.
Write out that
There. What?
as long as
Sure.
the particle is moving, as long as the particle is moving
See.
with constant speed
Good.
in a particular direction,
The thing. Good.
its acceleration is zero.
It.
Means it is in equilibrium. Means it is in equilibrium.
Means that.
It is, as long as the particle is moving with constant speed in a particular direction, its acceleration is zero. Means it is in equilibrium.
You did it. But there to show. Such a stupid.
Okay,
I went nothing.
now write down.
The young.
That's why net force on the object is zero. Net force on the object is zero.
I was like. You went. Run with nothing to it.
So, total work done by all the forces, can be calculated in two ways. Total work done by all the forces can be calculated in two ways.
How did you? What? We.
First,
That's it. You know, then.
calculate
You swim well. Like.
the work done by individual forces. Calculate the work done by individual forces and add them
I could still be in the. Which was.
to get zero. Add them to get zero. Okay.
Good.
Next,
Good.
calculate
With that. Why not?
second method. Second method is calculate the resultant of all the forces. Calculate the resultant of all the forces
Yeah.
and then multiply it with displacement and then multiply it with displacement
They made a David then.
to get the total work done. To get the total work done, zero. Means in either way total work done will be zero if it is moving with constant speed.
Well, yeah. Hey. Good.
But remember, all the forces has to be taken. If you miss one of the forces, then it will not give you the correct answer.
I said that you.
Okay? Now,
Make it. Take. It was like the things that you first went to the kitchen. You know, no, it's really fun. I just found out I that. When you do it, I'm not feeling. Basically, playing. But it's tough to play. And first I feel strong. That's. You know, this feeling. So I'm cooking. It's a sense of. There's like a sweet stuff. And it's quite good.
so we consider there is a mass M hanging by a light inextensible cord. Massless inextensible cord. It is hanging from the ceiling. Now,
I mean,
This angle with the particle initially is 0 degree. Now you pull the string, pull the mass with a constant force. No, sorry. You pull the mass with a variable force. F is variable.
In some way,
Variable force.
very but without function at the
Up to this point such that the string makes an angle theta with the vertical line. Such that the string makes an angle theta with the vertical line. And this force is always horizontal. This force is not along the tangent or anything. The force that with which you are pulling it is perfectly horizontal. The magnitude of the force is not constant, it is changing. So during that moment, what is the work done by this force F? Remember, this force is variable force. So you cannot calculate only force into displacement. The length of the string is given. Length of the string you can consider to be capital N.
Obviously, define that.
You cannot only calculate this displacement and multiply by the force, because this is variable force, and the formula that we discussed, F into S, F dot S, that is only valid for constant forces, forces with constant magnitude. So here the direction of the force is changing, same, but it is mentioned that the force is variable. Then how to solve the problem? You have to use that logic since it is moving with constant speed. But previously, when I showed that lifting up of a box or any mass, that is a one-dimensional rocket that is moving along a straight line. Now it is moving on a plane. It is a two-dimensional rocket. Good morning.
Just go through little see when it's lit and then just up the like the classes good. What I it's a short means and thick lines but it's measurable. Once you do stuff like loading just use your setting cooking Android for you. ABC. She you know what he good insight. Well, this is what I'm because he has to look to 14. She loves that.
Speed is constant. So I can still dodge it.
Then you are in the ground.
Very good. But mass is constant.
But it's time for minutes.
Constant speed. That is also in chapters about basketball with constant speed. So kinetic energy is half a. So hence variable force must be captures by some other variable force in the variable existence. So that will capture the total force.
No. You can do a little bit of that thing with numbers. Doctor, Rachel, these things. In fact, letting in the view, we couldn't show these things to the left. Use it to not to the left. You choke line. I think the much of the organs feel like my leg just left. So let's get you the variation. Giving enemies to baby. I did it. Get on the bench. Get on like two big side. What then? Goodness. And do it with me. With that well, see. And we can ask one little turn or to believe that look to the let's have no. Sorry, I can do the opposite. Well, so I'm gonna do this.
variable force means the value will change.
Nowadays, joke.
Yes, direction is fixed in the horizon itself, but always its magnitude will one.
Ship one so they get it.
Now see first.
Goes full again.
In this problem, it is mentioned that force is variable. If this F is given applied force given horizontally always, that's variable. Then the magnitude of the force will change. But then how the mass can move with uniform speed? That comes into the maths. That's how the mass will be moving with constant speed. Because we know that variable speed means always some acceleration with and the magnitude of velocity and direction of this magnitude of velocity can not remain constant. Now think of it that though the force F is variable, if there is some other variable force acting on the mass and that is equally varying to cancel the effect of the variable force F, then net force is again, we can zero for any particular position in equilibrium and we can consider that it is moving with constant speed. Now, what are the other forces acting on the mass in this situation? One is F, that is variable force. One is mg, another is tension of the spring. So can mg be changed? No, because pendulum is not moving that up to a great height like radius of the artery is moving. So mg is not changing, that is constant force. So the other force that can bend, that is tension. So the tension in this force is the variable force which will cancel the variation of F such that the system can move with mass can move with constant speed. Until tension cancels the variation of the applied force F, the system cannot move with constant speed. Here, now we will draw the friction force and all these things, and we will draw the force diagram, and that's how you compare. See. So I will remove all these things from here.
So we will
Check. I will draw the passes as if they are point passes.
with
Like this. So one force is acting along this direction. Make it some bigger. mg. There is one tension along this direction, and there is this variable force F. Yep, in this equation. Now let us consider this is an arbitrary position. This is an arbitrary position.
How it should be modified to say
Means this one is that theta
others
up to which we can move, and this position is an arbitrary position, some alpha.
this is what the range of
So I consider that the range of alpha is varying from 0 to theta. That the variable and the number I have changed. Suppose it is given in terms of theta, then say 0 to pi by 2 it is moving. So for that integration part, I write it as alpha. Now alpha's minimum value is 0 and maximum value of the alpha is theta. Denoted. Suppose 0 to pi by 6, 0 to 30 degree. In this manner. You can also write in theta and vary theta from 0 to theta, but I write a different variable. Okay? Now, in this situation, split the forces into components. This angle should be alpha then t cos alpha,
Probably good, but
t sin alpha, t cos alpha, t sin alpha. Since speed is 0 at every point for the movement of this particle, net force should be 0. So net force should be 0 will give you t sin alpha equal to f and t cos alpha equal to mg. Okay. Now dividing these two we will get tan alpha equal to f by mg. So divide these two, get tan alpha equal to f by mg.
Like if it's
Then f equal to mg tan alpha. Now see what is going on. Body is moving in this path. Then what will be its displacement along x direction? Let it be dx. And what will be its displacement along y direction? Let it be dy along x direction and y direction. This is dy, this is dx. Then from the definition of the derivative you know that dy dx equal to how much? Tan perpendicular by base, that is tan theta. Perpendicular by base means tan theta to. You don't know trigonometry.
Yes, sir.
So perpendicular by base, what is called? That is tan theta. So in that case theta is considered as alpha. So dy dx equal to in this case tan alpha. Okay. Then from this I can substitute the value of tan alpha over here. Then first calculate the work done. Due to this force I have to calculate work done, and due to this force the displacement in which direction? X direction. So for small displacement work done is f into dx. F into dx. Then the total work done will be integral f dx from 0 to theta. Limit is given 0 to theta. Then put the value of f. F is mg tan alpha. What is tan alpha? dy dx into dx. Integral 0 to theta. But mg is constant.
Wonderful.
So it is integral 0 to theta ty means up to this point. Now up to this point what is the displacement in y direction? This is y, but we can calculate y simply by the geometry without any integration. From this point draw a perpendicular on this. This length is L. This total angle is theta. So what will be the length on this part? That we have discussed in the problem of sphere when an insect is moving inside the sphere. If this is L, this one is theta. This side will be L cos theta. Because this angle theta, this is perpendicular drop. So this part will be L cos theta. So what will be the remaining length? L minus L cos theta.
Alternative. Which are what?
L minus L cos theta. So this is the value of y. Then I will be substituting for this integral. Don't need to solve the integral. You have to only consider that the total length will become y when angle becomes theta. Because this increases, this is increasing up to this. So that will become y. So this is y. So from this point drop in perpendicular. This length is L. So this is L cos theta. This one will be L minus L cos theta.
Right.
So just put it. So this one will become mg into L into 1 minus cos theta. L minus L cos theta, L common. So it will be L into 1 minus cos theta. Now, this is problem is solved by applying the net force to be 0, and that is calculated from the equilibrium by applying the free body diagram, and then we have to integrate and do all these things to solve the problem. And it is a very difficult method, and it will never come in medical statistics. So this problem may come in medical entrance exam, but if you use this procedure, then you have to leave some other question. Means there is some other technique to solve this problem quickly, and very quickly that given you cannot imagine. The same result I can get, but without doing all these free body diagrams and anything, I will do nothing and write the answer directly. And I will explain how can it be solved. Hardly take 30 seconds or less at that. See how. This is written. Okay, so I will erase. Down. Check it once again.
I'm trying to keep one to the answer person. Going back to least check. And back remember. Well, actually, let's find out. Just kidding. Yeah, that's
see, the body is moving with constant speed. So will the kinetic energy of the body change? No. So total work done by all the, and each point of the body is in equilibrium. So what is the total work done by all the forces? So I can write work done by tension plus work done by applied force F plus work done by gravity, all equal to Q. Okay, that I have written for the first problem when we are moving along the object along the straight line. Now check.
Got
What is the work done by tension? It is always 0. Because the body is displaced momentarily along the tangent to the path. Displacement is along tangent at every point, and tension is radially inward. So what is the angle between them? 90. So tension is a no work force. Tension is a no work force, because since it is moving about this point as a center, so this one you can consider as centripetal force. Centripetal force is always perpendicular to the tangent, and so the tangent is the direction of displacement, so it's a no work force. So work done by the tension will become 0. Okay, then I can write WF
Yeah, no, please.
plus WG. This should be equal to
But what does it?
0. Clear? Now, what is the work done by mg? How much it is rising? This side. That is,
What will tell you?
suppose y. This angle is theta. This length of the string is L. So just do this geometry. This is L. So this part will be.
Yes.
So what is the length of this part?
This is a fortune, man.
That is equal to y.
It's a keep it.
Direction of y is upward. Mg is downward. So write this goes. WF minus plus mg into L minus L into 1 minus cos theta
Keep it.
into cos
Keep it.
1 mg.
Look it. Let's put it. But
Work done by the force equal to mg is downward, y is upward. Particle displacement work done by mg we are calculating. Mg is downward and body is displaced by how much amount in upward direction? Y. And y, by dropping a perpendicular we can calculate the value of y. This length is L, so this part will become L cos theta. So this part should be L minus L cos theta, which is equal to y. What is the value of cos 180?
minus right.
Minus 1. So what is the work done by W of this force? That is minus sign will be there. It will come on this side. So it will become plus mgn into 1 minus cos theta. That is the answer.
That's a question.
So only you have to calculate the work done by gravity and take its sign to be positive. That is the work done by F. So no need to calculate the work done for F directly by integrating or anything.
It's in comparison. Supposed to him. What is the
See, we know that since the body is moving with constant speed, so no kinetic energy change. So total sum of the total work done should be 0 as before. So we can consider work done by tension. It is a normal force, so 0. So work done by F and work done by gravity should be 0. So what is work done by gravity? mg downward, it is moving in y direction, how much? Y. So from calculation of y in terms of length, I can drop a perpendicular here. It will be then L cos theta. So this will be L minus, that is equal to y. So in place of calculation of the work done by gravity, I write mg into y into cos 1 xt, because y and mg are oppositely directed. That is minus 1. So when this side there is a minus 1, I will take it on the other side. This will become plus. I haven't write the minus here because I put already 180. So you can also erase this part and write here directly minus 1, and then you can write directly.
stopping the list?
So that is the work done by the applied force. Because for calculation of the work done by the force F, no need to calculate F dot dx and then integrate. You can also calculate it by calculating the work done against gravity, since the entire mass is moving with constant speed. Now, why this method is easier? Because earlier the force F is variable. So integrating it will be something difficult and calculations are required. But in this part, work done by force is calculated by the work done provided by gravity, and gravity is not variable, it is constant force. So we can find the displacement and directly take the product, no need to integrate this.
And then the other.
So don't think that this technique, that constant speed means sum of all the work done should be 0. This is added only for linear motion. First problem is for linear motion, now it is for two-dimensional motion. It is also valid.
No, so.
So whenever you get same speed, you can apply this.
We should have
I haven't mentioned one thing. Same speed means net work done
Then we take the chicken.
0. And if the speed is not same, net work done is not 0. We can say that net work done equal to change in speed, change in kinetic energy. That is called your work energy theory. I haven't mentioned that, but I use it. The same principle of work energy theory. Where speed is not varying. Speed is not varying means what's the kinetic energy change will be 0. Then work done will be 0. And in all such problems, speed is given constant. Means it is a part of the work energy theory. Okay. Now the work energy theory I don't have to go. So this proof is known to you, all of them. So I will directly write the theory. That is work done by a force equal to half into m, suppose v2 square minus half m v1 square. Here, this one is your work energy theory. Says that change in kinetic energy equal to work done. And previously, the two previous problems are with constant speed. Means half m v square minus half m v1 v2 square minus v1 square will become 0. Because v1 equal to 0. Because all the cases are given with constant speed. Means change in kinetic energy will become 0. So work done is obviously 0. So that's why in all the cases of the previous two problems, I consider total work done will be 0. And calculate. Okay, now we consider if the velocity is not constant, speed is not constant, then we cannot set total work done 0 because change in work done equal to kinetic energy. Now, suppose and a bomb is there. Suppose you are sitting, on a chair, and can you lift yourself without putting your legs on the ground?
God.
Means you cannot accelerate yourself by using internal force. Because as long as your foot is not attached to the ground, you will not getting any external force to lift the chair. So chair and you can be considered as the same system. And all the forces applied by you on the chair to pull it up will be an internal force. An internal force cannot produce any acceleration or change in momentum. Okay. Internal force cannot produce any change in momentum. But can internal force produce any change in kinetic energy? Can internal force produce any change in kinetic energy? Yes or no? Cannot change momentum. You are eager to say that momentum P, kinetic energy, suppose K, then P square equal to 2mk. Okay? P square equal to 2mk. Kinetic energy, if momentum is not changing, we consider momentum 0, kinetic energy will be 0. I am not saying that momentum is 0, I am saying that change in momentum is 0. If there is no internal force, then momentum is not 0. Change in momentum is 0. Then can kinetic energy come? Now you will argue that if momentum is related to kinetic energy, then this change should be related to the kinetic energy. So if momentum change is 0, the kinetic energy should be 0. But think about it, when you write this formula, P square equal to mk, you are talking about the momentum of a single particle. Now I am giving you one example. Suppose a bomb explodes. Is there any external force on the bomb? No. So different parts are fragmented in different direction, and you apply conservation of linear momentum to solve this problem. Because there is no external force, so net momentum before collision, before explosion, and net momentum after explosion are equal. So there is no change in momentum. Explosion, all the parts are moving with some velocity. So kinetic energy and comes. S is not zero. And you can say that, okay, sir, if it is moving with in this direction in certain momentum, in this direction in opposite direction in certain momentum, the sum of the momentum is zero. But that is zero because it is a vector quantity. If it is mv on this direction, if it is minus mv on that direction, their sum can be zero. But for kinetic energy, half mv square, half mv square, and square will come. So it is no more negative. So sum cannot be zero. So even if initial momentum is, initial kinetic energy is zero, and only system is acted upon by external force, internal forces, its kinetic energy can change. Because you have already learned thermodynamics that internal energy can be converted to the mechanical energy. Internal energy can be converted to mechanical energy, and kinetic energy is just the one form of mechanical energy of the system. There is another form that is called the potential energy. So bomb explodes means initially it has internal energy in the form of chemicals, chemical energy. So that chemical energy is now converted to kinetic energy. So whether external force is there or external force is not there, that affect only the changing momentum. If external force is not there, change in linear momentum will be zero. Means momentum of the linear momentum of the system will remain conserved. But if there is no external force, in this situation, still kinetic energy of the system can change. So write it. External force zero on a system. External force zero on a system will ensure only its momentum is conserved. Its linear momentum is conserved. But it cannot ensure that kinetic energy of the system is conserved. Cannot ensure that the kinetic energy of the system is conserved. Because even if external force is not present, kinetic energy can change because of the conversion of the internal energy. Because if external force is there, then this external force will do some work and the kinetic energy can change. But if external force is not there, the internal energy will convert to the mechanical form and produce kinetic energy. So kinetic energy can be changed by internal forces also and by external forces also. Okay. Now, next, we have considered that a particle is moving and it is acted upon by some force. Initial velocity is given v, and after the action of some external force, we consider that the velocity changes to v. Now, this one work energy theory will give that work done by the external force on that particle will be half a v2 square minus half a beyond square. That is the difference of kinetic energies. Now we are considering external force only. Now this external force can be given by some external agent. It may be earth, gravity, it may be electrostatic force on a charged particle, it may be your applied force, it may be the tension with which you are pulling. Something, many forces can be there. Now, if the force which produces this change in kinetic energy, if that force is called conservative force. Conservative force. Now, what do we mean by conservative force? What do you mean by the term conservative? Not needed any physical explanation, any physics topic. Only the term conservative.
If space was not taken to me, you'd say,
Suppose there is a community which is called very conservative. Means they have certain rules and they are bound with that rule, they will not break that to it. That is called the conservative community. Suppose some communities are there which do not allow intercaste marriage. Intercaste marriage is not allowed by a particular community. So today we call those communities conservative communities. They have some conservation. Similar to that, there are some forces who are very conservative with respect to something, and some other forces are there which do not have that kind of a limitation. They are free. So with respect to that, it is defined in terms of whether the system allowing mechanical energy and the other form of energy also, or only the mechanical energy. Okay. So for a particular system, we can apply certain energy to those system. It may be in mechanical form, it may be in non-mechanical form. The system can release energy in mechanical form or in non-mechanical form. So there are certain class of forces which allow only transfer of energy from a system to other system only in mechanical form. Means non-mechanical form is not allowed, like the intercaste marriage is not allowed in some community. Same thing, there are certain class of force which, when acting on a particular system, from that system energy can come out or energy can come into the system only by mechanical energy, as a mechanical energy, means either kinetic or potential, but not like heat energy, not like light energy, not like sound energy, or whisper. And non-mechanical form, the non-mechanical form transfer is not taking place. It is not allowed. It is completely prohibited by some force. So the forces which have this nature of only producing mechanical energy and not allowing any non-mechanical form of energy is called conservative force. And the forces which allows both mechanical energy, non-mechanical energy, both, they are more liberal. They are called dissipative forces or non-conservative forces. So write down. Some forces are in nature which allows only mechanical form of energies, which allows only mechanical form of energies to exchange between
Quite.
Mechanical forms of energies to exchange between system and surroundings. Between system and surroundings.
With that.
Okay?
It's that out of learning.
And these forces are called conservative forces. These forces are called conservative forces.
Thank you.
Example,
The truth is that's down.
write down the first one, gravitational force in weight. Gravitational force.
Yeah, that's the check.
Electrostatic force. That is Coulomb's force that you have studied already. Coulomb force, that is electrostatic force.
Yeah. Yeah, that is.
Spring force, calculated by Ohm's law, F equal to minus kx. Spring force. All these are conservative forces. Now,
Sure, I fell.
write down. There is another class of forces. There is another class of forces which allows the exchange of energy, which allows the exchange of energy between system and surrounding. Between system and surrounding, both in mechanical and non-mechanical form. Both in mechanical and non-mechanical form.
Thank
Okay. Those are called non-conservative or non-conservative or dissipative forces. DISSIPATIVE, dissipative forces. Means energy can dissipate from that system. Example,
Action.
friction force. See, if I rub these two pumps one against the other, then there is kinetic energy provided by me,
Yes, that.
and with which kinetic energy I can move it. I cannot move it with that much kinetic energy because it will generate, means energy will dissipate from this system in the form of non-mechanical form, that is called heat. So this force friction is produced allowing the energy transfer by a non-mechanical form. Not only allowing kinetic and potential, it will allow heat energy. So this is a non-conservative force. Okay. Now, give me another example of non-conservative force.
Discuss with me. Discuss with me.
Viscous force. Viscous force. Write down one more example. One more.
Okay.
Magnetic force. Defined by Q into V cross B. That is also
That's the
non-mechanical force. Just write the mechanical forces that I have said in mathematical form. First one, I said gravity.
Ability.
I write in vector form.
Hi.
Okay? Minus G mm by r square r cap. This is the force of gravity.
Take care.
Two forces. charged particles by r square r cap.
into the blood is secretly. Remember that.
That is,
There is time.
which force? Electrostatic.
Volume smart. TV.
Then minus kx. That is the force exerted by spring, deformed spring, elastic force.
He was then back to complete.
And now I write these forces. F equal to
And the so
6 pi
the second is
theta on E. This force is
escape for
viscous force. This law is Stokes law.
keep
Stokes law. And this V is called the terminal velocity.
so right.
Stokes law. When suppose a water drop falling through air, when it achieves the terminal velocity, at that moment what is the viscous force of air acting on it? It's just like a friction. Liquid, solid, liquid friction. That is, fluid friction is called viscosity. And this F equal to this formula is directly means 6 pi eta RV, where R is the radius of that droplet which is falling. V is the terminal velocity and R is the eta is the coefficient of viscosity of that medium.
Love.
Okay. Now, another force is, I said, magnetic force.
You should
Magnetic force F equal to Q B cross A.
stay with
Okay. Now on the left side, those forces all are said to be which type? Conservative. And on the right side, the forces are dissipating. Now, can you identify the structure of the force and can say that okay, this force has some similarity and that those other forces which are dissipating have some similarity? Check carefully. By looking at the equation of the force or the form of the force, you can identify which one is conservative and which one is dissipating.
We can continue the place of the actual picture.
See, mass. Is mass a kinematic quantity? No. Because in kinematics there is no concept of mass. Concept of mass comes after Newton's first law. That is a dynamical property, inertia. Charge, is it a kinematics property, kinematical property? No. Kinematical properties are what? Displacement means position, velocity, acceleration. These three are kinematical quantities to define the motion of an object. Now, other things are the properties of the matter. Charge is a property of matter, and viscosity is the property of the liquid or the fluid, and all these things. Spring K is also a property of the spring. The spring constant, force constant of spring. Now see, here this force is depending on which kinematical property? Kinematical quantity?
One
R means position. Here in Coulomb's law, this force depends on R, again on position or displacement. Here, this F in Hooke's law depends on displacement. So as long as force is only depending on displacement, because these forces are conservative and they can only lead you to mechanical energy. They will not allow any non-mechanical form of energy. And see this one.
How do you take on?
These are not depending on position. These are depending on velocity. So velocity dependent forces are always dissipating. They will produce other form of energy. That is heat, sound and all these things. That's why velocity dependent forces are always dissipating. Position dependent forces are always conservative. So by looking at the structure of the force, we can immediately say whether a particular force is dissipating or a particular force is
conservatively used.
Sir, magnetic force we can also write as BIL.
okay.
Sir, magnetic force we can also write as BIL. That's how we.
Then if you are writing in the form of height, if current flows through a wire, then there is duality. Heat energy is produced. I square RT.
Used to say here.
Okay.
Why did I get
So if you consider the velocity dependent forces, always write it is dissipating, because velocity dependent, under the action of velocity dependent forces, mechanical energy of the system will dissipate in the form of heat or in any other non-mechanical form. But if you consider only position dependent forces, that is gravity, that is electrostatic force, spring force, in all those cases the system's energy will be either kinetic or potential or transfer between them, that is mechanical form of energy. Clear? Now we will consider that an object is dropped from this position over the ground, and we consider it is falling only under the action of gravity. No other force is there, only under the action of gravity. With air friction, air buoyancy, all these things are neglected. They are not present. Then, if I consider that when the body will comes to this position, it will achieve some velocity. So let us consider velocity of this body downward. Here is v1. Now when this body comes to this position, suppose ground is here, it achieves some velocity v2.
Sure.
So velocity is increasing. Velocity is increasing because it is falling under the action of the gravitational force. So since the force is there, the velocity will also increase. Then I can write that work done by gravitational pull is half m v2 square minus half m v1 square. Work done by gravity, because gravity is acting in which direction? Downward. Displacement of the body is also downward. So it is half m v2 square minus half m v1 square. That is coming from work energy theorem. Now we can calculate this work done by gravity by using directly the formula force into displacement. Okay? See, suppose the height of the body at this initial position above the ground is h1 and height of the body above the ground at this second position is h2. Then I can write this work done equal to force of gravity that is acting downward mg, and what is the displacement of the body from this point to this point, that is h1 minus h2. This is the displacement of the body. Okay, so can I write here mg into h1 minus h2? So this is the displacement of the body in which direction? Downward. So force and displacement both are in the same direction, so work done is positive by gravity in this particular case, because the body is not moving up, it is falling under the action of gravity. Now you can write this one as W equal to mgh1 minus mgh2. Now this mgh1 and mgh2, these are the form of gravitational potential energy. So mgh1 is the gravitational potential energy of the particle or of the object at point 1. mgh2 is the gravitational potential energy at point 2, since first position, second position. But both are the expression for work done. So I can equate it and write half m v2 square minus half m v1 square, it is equal to mg h1 minus mg h2, because this is the expression for W, that is also the expression for W, so we equate this. So half m v2 square minus half m v1 square, that will be equal to mg h1 minus mg h2. Then we can write here, what is the meaning of this step? Means increase, the body is falling down under gravitational force, so its velocity will increase because of the acceleration due to gravity. Velocity increases means kinetic energy will increase, so it is the increasing kinetic energy. And height decreases means potential energy will decrease. So increasing kinetic energy equal to decreasing potential energy. This is the significance of this slide. Just write increase in kinetic energy
and
of the particle, increase in kinetic energy of the particle is equal to the decrease in gravitational potential energy of the particle is equal to the decrease in gravitational potential energy of the particle. Right?
that's good. We do. Much of them.
Then the next step I can write half m v2 square plus m g h2, that is equal to half m v1 square plus m g h1. Okay, all the quantities having 1 is taken on the right side, all the quantities having 2 as a suffix is taken on the left side. Then this represents kinetic energy of the particle at point 1. This represents potential energy of the particle at point 1. So sum of these two is giving the mechanical energy of the particle at point 1. That is equal to mechanical energy of the particle at point 2. Means
that
there is other form of energy is not generating. So this is called the conservation of mechanical energy. Means if the force is gravity or electrostatic or any type of conservative force, then at each point of the path, total mechanical energy of the particle will remain constant. That is called conservation of mechanical energy. Conservation of mechanical energy. You can also say that this format, that change in kinetic, increase in kinetic energy equal to decreasing potential energy, which total mechanical energy is fixed. A part of it is kinetic, another part of it is potential. So if one will increase, the other will decrease, but the total sum remain same. That is called the conservation of mechanical energy. Here, if the friction comes, then sum is converted to the heat. That means initial mechanical energy is always greater than final mechanical energy because some energy should be transferred to heat. So only when dissipative forces comes, mechanical energy conservation will not complete and it will not obey. Okay? So now we have to discuss some problem.
Is it leaky or expensive?
Write down.
Listen, look under the titties. So, there's a fact that
A particle is dropped from a height.
I'm not for sure.
10 meter
Round it.
over the ground.
Put it in.
Just before touching the ground, its velocity is 9 meter per second. Just before touching the ground, its velocity is 9 meter per second. Find the work done by air friction. Find the work done by air friction means air resistance. Mass of the particle is 2 kg. Mass of the particle is 2 kg and small g is equal to 10 meter per second square. Just a minute. What is the velocity given? No, not 9. It should be 8. 8. I mean, just a minute. Just a minute.
And hit.
7. Right. The velocities I have to adjust.
It is good question. You job you important session. But that's required to routine and fix the this time to do. We need to get simple needs to then they get so what is the I yeah that was trace station and search. This on yeah.
Just before touching the ground, its velocity is 7 meter per second. Find the work done by
friction. What? It will. Down it should get me. Two. So maybe that's got a good foot. But they put you. Yeah. So really which is an accurate. But then I should be good drive with them. You would all different. Place looking like
So first calculate what is the total mechanical energy at the beginning. At the beginning, it is about to released. So what will be its velocity? 0. So its kinetic energy will be 0. So entire energy will be potential. So calculate that mg first position. So in the first position, if I calculate this one, so this one is the first position. Now it is said that it is released. So V1 will be just released from this position. So V1 should be 0. So in this situation, kinetic energy half of V1 square will be 0. But what is potential energy at this equation? Mg H1. H1 is the height from the ground in this case. So right, potential energy Mg H1. What is this value? M is 2. G is 10. H1 is given 10. So its value is coming 200 joule. So what is the total mechanical energy? 200 joule. Because 0 plus 200 is 200. So total mechanical energy at point 1. I write T1. Okay. Total mechanical energy. It is 200 joule. Now calculate the total mechanical energy at this second point. What is kinetic energy at this point? Given half m
14,
v2 square. Now calculate half
14.
m is given 2, this is given 7 square.
Then
So that is 49 joule. What is potential energy at this point? It is mentioned as ground.
0.
Means height is 0. So H2 becomes 0 and MgH2 is already 0. So can I write the total mechanical energy at this point as 49 joule?
Is the effort?
Because it comes just close to the ground. Close to the ground means height you can consider to be 0. So now the potential energy is 0, but kinetic energy is only there. That is half into mass into speed square. Speed is 7 now. So is T1 and RT1 T2 equal? No. So the difference occurs because some energy is converted to heat energy or something due to air friction. So how much is the work done by that air friction? Difference of these two.
Find that 0.
So work done by air friction. So W friction. That will be initial kinetic energy minus final kinetic energy. The subtract.
It's
It will be 151 joule. Okay. So total kinetic energy here this 200 joule. Just before touching the ground, total kinetic energy becomes 49. So where the rest of the energy goes? It goes as heat energy due to air friction. So difference of these two kinetic energy, mechanical energies will be the work done by air friction. Okay? Understand?
We should have been with the
Understand?
Yes, Singapore.
You don't. Okay. What is the velocity given here?
good. No, we don't.
0. Why? Because it is just released. So what is the kinetic energy at this point? Half m v1 square. So v1 0 means this entire term is 0. It is at a certain height above the ground. That height is given 10 meter. So what is potential energy? Fg, H1, m is there, g is there, height is there. So potential energy becomes 200 joule. Total mechanical energy means kinetic energy plus potential energy. So 0 plus 200 will be 200. Now, the body is released. Another situation is given just before touching the ground. Its velocity is given. How much? 7 meter per second. So it has kinetic energy. So it will be half m v2 square. So half mass is given 2, velocity just before touching the ground is given 7. So it will be 49 joule. But just before touching the ground, what is its height above the ground? Almost 0. So now potential energy will become 0. So what is the total mechanical energy at this point again? 49 joule. So what is the loss in mechanical energy? 200 joule minus 49 joule. That is 151 joule. So where this loss in mechanical energy goes? It is lost from the mechanical form. Means it goes to non-mechanical form. Non-mechanical form comes due to air friction here. That is heat. So work done by air friction will be loss in mechanical energy. So write this one. Work done by any dissipative force or work done by all the dissipative forces. Work done by all the dissipative forces is equal to loss in mechanical energy. Loss in mechanical energy. It is always true. Work done by all the dissipative forces will be equal to loss in mechanical energy. In this case, how many dissipative forces are there? Only one. Air friction. So work done by air friction will be loss in this mechanical energy. Okay,
So I think this is what it does. And do it. What's that? It's sticky.
clear?
It's
Now, next problem.
it's the kind of it's a most practically I can keep it without music.
That is a very common problem. We have discussed this one in related to projectile motion. That questions I have given to you. There is this problem. A particle projected at an angle 60 degree with horizontal. A particle is projected at an angle 60 degree with horizontal with kinetic energy K. What will be its kinetic energy at the topmost point of its path? What will be its kinetic energy at the topmost point of its path? Means in terms of K, you have to find K by 2, K by 3, K by 4, K by 5, whatever.
This shot to this side. This is now red or one service. Very simple.
Acha, okay. Find the kinetic energy of the particle at the topmost point of its path. Boss, says,
What's the story? If what is the done? Connect that.
he by 4.
So it's very to
Cos 60 will become cos square 60 is 1 by our.
Dear she what? With a just put you and it's that you have a big body picture. Laughing like the next lanterns.
See, this is the path of the projectile.
Yeah.
Okay, this one is the path of the projectile. It is said that it is projected with certain speed.
The cowbell.
Say you, this angle is given, suppose theta. Let us we will put theta equal to 60 degree. What will be the velocity of the projectile at this point?
He has lost it.
U cos theta. Because topmost point means only velocity is horizontal. Vertical component of velocity will become 0 at the topmost point. Because if it is not 0, then it will reach more height.
Back on.
And it is mentioned topmost point. Top means it cannot reach further up. Means at this point vertical component of velocity is 0. Entire velocity is horizontal. And horizontal velocity is unaffected by gravity. So initially if it is u cos theta, at any point it will remain u cos theta. So this at this point kinetic energy is given K, that is half m q square. No need to bother with any direction or anything because kinetic energy is a scalar quantity. Clear? Now kinetic energy is a scalar quantity, so it is just half mu square. Now at this point there will be some kinetic energy, so it will be, say, K prime. It will become half m into velocity at this point is square. So u cos theta whole square. It will become u square cos square theta. Then what is half mu square? K. So in place of half mu square I can put k, and this is cos square 60 degree. Cos 60, what is the value of cos 60? 1 by 2. So its square means 1 by 4. So it will become k by 4. So kinetic energy will at the topmost point will be 1/4 of the initial kinetic energy. Kinetic energy at the topmost point will become 1/4 of the initial kinetic energy. Okay? So initially velocity u, mass m, so kinetic energy is half m square. At the topmost point it is half m. U cos theta is the velocity there, so it is half m u cos theta whole square. So we get half m u square cos square theta. Now half m u square from this equation is equal to k. So in that equation, in place of half m is u square, I put k. So it will be k cos square theta. Theta is 60. Cos 60's value is half. So its square will be 1 by 4. So kinetic energy at this point will be k by 4. All of you understand?
Next year.
You and don't laugh. At this topmost point, is it at rest at the topmost point? You throw something, it will go to the topmost point and then fall. Will it fall? Topmost point, which component is 0? Vertical component. But horizontal component we have still present. So is the total velocity 0? No. Kinetic energy equal to half m into magnitude of velocity whole square. So is the magnitude of velocity 0? No. The velocity that is in any direction that you have to calculate. Okay. And you cannot say that vertical kinetic energy is 0. Because kinetic energy is scalar. So you cannot split it into components like vertical and cast. So if at this point it is totally 0, then I can say that body will come to this point and then it will not follow this path. It will come to this point and okay. So don't argue that at the topmost point of the projectile velocity is 0, because at the topmost point then you throw something, it will come here and stop. Have you ever seen this kind of a thing? It will come here and stop after throwing. You are throwing like this. So it will come to the top and then stick to it. In fact, is it possible? No. So at this point velocity is not 0. So how can kinetic energy at this point become 0? Yeah. You. Tell me, what is the problem? So is this u cos theta velocity ever change? No. Why? You forget all the things. This velocity in which direction? Horizontal direction. And gravity is in which direction? Vertically downwards. So what is the angle between horizontal and gravity? 90. So a vector has no effect on its perpendicular direction. So being perpendicular, gravity has no effect on the x direction of velocity. So x direction of velocity is constant. So if it is here u cos theta, then at this point it will remain u cos theta. And initially what is the upward component of velocity? U sin theta. Gravity is there. Gravity is in the opposite direction. It will try to decrease the upward component. So at the topmost point, upward component of velocity will become 0. So it cannot rise further. So that's why it is called
Seven.
the upward component of velocity. That's why it is called the maximum height. Because in the upward direction, it is going with a certain velocity. And due to gravity is acting in the opposite direction, means it starts to retard. Then at the topmost position due to retardation, this velocity goes to 0. So it cannot rise further. That's why you are saying that this height is maximum height. So at this position, what is the velocity? U cos theta only. And at this position, U.
20.
So kinetic energy at this position will be half L
See the middle plus
U square. That is given as K. At this position, this is velocity. So what is kinetic energy? Suppose K prime, it will be half M U cos theta whole square equal to U square cos square theta. How much is the theta's value given?
60.
Then you can write half M U square means K. So write it K cos square 60 means 1 by 4.
Equal to
So as this velocity component decreases, so the velocity decreases as the particle is going up. So kinetic energy will also decrease. Initially kinetic energy is high because there are two components. At this point, velocity component is only one left, other component becomes 0. So total velocity decreases, as a result kinetic energy will also decreases because it is half L velocity square. So if velocity decreases, the kinetic energy will also decrease. So it will become 1 by 4 of the initial kinetic energy. Okay? So if you forget all the formulas of projectile, then how can you solve the problem?
significance.
So you have to memorize these formulas, those I have discussed previously. See, this is not a situation like you read one chapter, you read only those formulas, remember and forget all the previous chapters. This is not done. You have to remember all those topics first. When you give the examination, you have to you have to solve the question from every chapter. So if you forget something, it is not like a T20 match, it is like a test match. You forget today's chapter, you forget yesterday's chapter and whatever you are doing in this today. If you have one chapter read today, then tomorrow you know this chapter what is going on, and if the chapter that is completed 7 days before you forget, then how can you give the examination? Okay, so for that every chapter's formula, at least those formulas you have to remember every time, such that whenever any particular situation, it may happen that some difficult problem you may forget and before exam you revise and all this. But the basic concepts, the basic formula, like the formulas of kinematics, the Newton's law formula, the component bringing, sin theta, cos theta, all this, these basic formulas you have to remember always, such that anywhere where it is used, you can use that. Okay? So just do one thing. It is a very good technique. Write all those formulas that you have studied in kinematics. Okay, many formulas you studied in kinematics classes. In probably there will be many formulas. Write it in a big paper. Okay, the kinematics formulas, the Newton's laws formulas, the projectile motion formulas, the circular motion formulas, friction, those formulas, write it in a big paper. And put it on the wall. Anyway, this is a technique, many students will follow this technique, and once every time when they are studying or something, okay, this one will follow, right? This one. So in this way you will be habituated to those formulas and you never forget. So this is a better technique. So otherwise if you write it in a copy or in a book and every time you will find Okay, there is too much writing, too many problems. What is that formula? Is there? Oh, okay, one formula is there.
Absolutely fine.
So in this way, you cannot remember the formulas. Write it at one place and put it in your bookshelf or anywhere, the reading table or over anywhere. And just once go through the formula. See, after 10 months you will give the exam. So almost 300 days left, I can consider. So in this 300 days, if once in every day, see those formulas, then it is automatically remembered. You don't need to work harder before the exam day to remember all those formulas. Clear? So do it, make it a practice. Then only you can. Because in the last day before exam, but suppose 7 days before the exam, if you are planning to recollect all the things, believe me, you can't. It is impossible. And then this type of situation, this type of actually this type of thinking will come that okay, I left the exam for this year, next year I can manage, and I will break all the barriers next year.
Super one.
I can do it. Then you will not be able to clear the exam in this year. Then in the next year, just after the exam is over, you will think this idea comes in your mind. Okay, 1 year left, many times. So I can relax right now. Then after that I will start. After taking rest for 1 month, then I will start. Already something is with me. How much to read? Again, before the exam date, 2 to 3 days before the exam, the same situation will arise. Okay, I can skip this year. Next year I will break all the things. I will break and get a record marks in it. The same situation almost. So start from the beginning. Otherwise, it is very difficult to clear any exam. Because exam is not tough. Exam preparation and mindset is very tough. First you have to be in a proper mindset that I will do all these things and I will arrange or assemble all the things together well before the exam. Not just before the exam. Well, in advance you have to complete all the things. So that's why make it a habit such that formulas will be very essential in the NEET. Because many questions will come which can be answered directly by putting the values in the formula. So formula you have let. It's not the JEE mains. If it is JEE mains or JEE advanced, then I will say, okay, forget about formulas. You have to only build over the concept, and from the concept, draw the keyboard diagram, all these things, and you can do it on the all. But in the exam, some techniques are required for just putting the values and finding the result. If you can't remember the formula, you won't derive this one. In the hall, in the pressure, you cannot derive, and even if you can derive, it will take too much time. And you have leave questions. Clear? Now,
Actually, myself.
see. So we have some other topics of this one, which is suppose there is a string, stretch, massless string and inextensible, and there is certain mass connected with the string, and this mass is moving in a vertical circle. Means this stone is tied to a string, you are holding the other end of the string and move it in a vertical circle. It is moved in a vertical circle. Now see, if you are moving it very loosely, it's a very small velocity. It may happen that it will move to the rise and fall on your head. Okay.
Any
Then you have to ensure a certain speed at the bottom such that at the topmost point it will not fall on your head, rather it can complete the circular path. So what will be the minimum velocity that you have to impart at the bottom point such that it can complete the circular path? Is this problem clear? What we have to do? I have to find out a minimum velocity at the bottom point of the circle such that the stone can complete the circular track. At the topmost point it will go and it will not fall on my head. Clear? See. So first write down the problem. A stone. This is actually a theory. I give it in the form of a problem. A stone is tied with string and rotating in a vertical circle. Rotating in a vertical circle. What will be the minimum speed of the stone at the bottom? What will be the minimum speed of the stone at the bottom? And at the topmost point. And at the topmost point. So that it can complete the circle. Okay? So that it can complete the circle. Now, to solve this problem, I have to take two positions then. One is the topmost position of the stone, because speed is required here also and at this point also. So I am considering that the stone is moving in this way. Now, at the bottom point, in which direction the stone is moving? This is the direction of the velocity of the stone at the bottom point. Okay. Now, at the top point, what is the direction of velocity?
This one combined.
What will be the magnitudes of those velocity at this point and at this point? Are they equal or different?
In caution.
First tell me this one. At the bottom point and at the top it is moving in a circle. So, what is the magnitude of the velocity at the top point and bottom point? Are they equal or are they different? Equal. Why? Because it is a circular motion. See, in the circular motion, is the magnitude of velocity always equal? No. It is equal only in uniform circular motion. Okay? Now, tell me, is it an example of uniform circular motion? If yes, then how? If no, then also how? In the last class, when we are discussing circular motion, I told you that in a uniform circular motion, there is only force that is acting towards center, called centripetal force, which produces centripetal acceleration only. But there should not be any tangential force, because tangential force will produce tangential acceleration. As a result, magnitude of speed will change. Clear? Tangential force will produce tangential acceleration, so the magnitude of the velocity vector will change, means it will be a non-uniform circular motion. Now see, is there any tangential force? Of course there are tangential force at some points of the path when the stone is moving. Suppose the stone is moving when here. What is the direction of centripetal force? That is given by the string's tension. It is towards
No, that's right.
center. Centripetal force is always towards center. So that means towards center. But there is gravity.
With a free.
It is giving a force in downward, tangential direction at this point. At here, all the points there are gravity, and gravity is not towards center always. So that is producing centripetal. Apart from centripetal acceleration, another acceleration is provided, that is tangential. And since there is tangential acceleration, we can say that magnitude of speed will change from top to bottom. So it is an example of non-uniform circular motion. So write it. In this case, the mass
What?
is not only acted upon by tension. Mass is not only acted upon by tension. T. Tension T. In the bracket write centripetal force. Because this tension is the centripetal force. Centripetal force. Okay. Gravity is also there. Gravity is also there, producing tension.